Particle P lies on a slope inclined at 30 degrees to the horizontal. P is attached to one end of a taut, light, inextensible string, which passes through a smooth ring at Q of mass m kilograms. The portion PQ of the string is horizontal, and the other portion of the string is inclined at 40 degrees to the vertical. A horizontal force of magnitude h newtons acting away from P is applied to Q. The tension in the string is 6.4 newtons, and the string is in vertical plane containing the line of greatest slope on which P lies. Both P and Q are in equilibrium. Calculate M. Calculate H. Given that the weight of P is 32 newtons, and that P is in limiting equilibrium, show that the coefficient of friction between P and the slope is 0.879, correct to 3 significant figures. Q and the string are now removed. Determine whether P remains in equilibrium. So let's have a look at the question, and I've got it summarized here. The tension in the string is 6.4. So let's start putting in the forces then. There's the tension here. There's also tension here because it's a smooth ring. This is of mass mq, so this is a force of mg. There's this h here. Okay, the tension is 6.4, so T equals 6.4 newtons. Okay, so and it's in equilibrium. So there's all the forces then. So let's do the first part then. Calculate the mass m. So let's resolve forces at Q vertically, shall we? So resolving forces vertically at Q. Basically we're applying the formula F equals ma. There's no acceleration, so the resultant forces will be 0. Gives. So vertically then, we've got T cos 40, T cosine 40 degrees, is equal to mg minus mg equals 0. So that tells us then the mass. So move this over, mg is equal to T cos 40. T is 6.4 from the question. Put that in. So it's 6.4 cosine 40. So m is equal to then 6.4 cosine 40 degrees divided by g. Type it in the calculator. Cosine 40 in degrees mode divided by 9.8 equals 0.500 to 3 significant figures. So there's the mass then that we've got. So calculate H. Well, let's resolve the forces horizontally now. Again, it's in equilibrium. So part 2. Resolving the forces horizontally at Q and applying F equals ma. The resultant force is 0 because it's in equilibrium. Gives. So what have we got then? Well, we've got H minus T of this angle, which is 50 degrees, equals 0. So H minus T cosine of 50 degrees is equal to 0. So that tells us what H is. T, move these both over and take the T out as common. 1 plus cosine 50 degrees, which is equal to 6.4 times 1 plus cos 50. So tap that in, we get H. 6.4 times bracket 1 plus cos 50 equals 10.514, 5138 10.5138, which equals 10.5 newtons, and that's the three significant figures. Okay, so there's H, that's part 2. Given the P has weight, so now we put in the weight of P. So it's got weight 32 newtons. It's going to have a reaction force, here perpendicular to the slope of R. So this is a perpendicular line here, supposed to be. Okay, it's going to have a tension here due to the string. And then when it's being pulled, it's got this force. It's going to have a frictional force here, acting up the line of greatest slope of mu R. P is in equilibrium, limiting equilibrium, so we've got mu R here. So that's what we've got then. That's 32 vertically downwards. This is 30, that's 60. So this is 30 as well. Okay, so now at P then, let's resolve the forces. So let's resolve them this way first. So this angle here, this is 30, so this is 60, isn't it? So we need to bear that in mind. And resolve the forces, part 3. So let's resolve them perpendicular to the slope at P. F equals ma then. That gives. Okay, so we've got our reaction force there. Minus plus this t cosine of this angle. This is 30, this is 30, so this is 60. T cos 60 plus t cos 60. Right, that's that force. Minus the 32 cos of 30. That's it. Minus 32 cos 30. And that equals 0 because there's no acceleration, it's in equilibrium. So that tells us what R is then. Let's move this over, 32 cos 30. Minus T. Tension in the string is 6.4, wasn't it? Just double check that. Tension is 6.4. So move this over is 6.4 cos 30. Cos 60 is sine 30 is a half. 6.4 times half is 3.2. So we can put that in straight away. So what have we got then? We got 32 times cos of 30 degrees minus 3.2 equals decimal 24.5128. 24.5128, which is equal to 24.5 to three significant figures. Newtons. So there's our reaction force then. Part 3. So now we can resolve the other way, and hopefully we'll get mu now. So resolving along the line of greatest slope. So let's do that then. Let's go up the line of greatest slope. So along the line of greatest slope now, at P, F equals ma gives. So we had mu r, which is acting up the line of greatest slope. Okay, minus t cos of this angle, which is 30, minus t cos 30. Yep. Minus t cos 30. Cos 30 is root 3 over 2. Minus the weight component. Let's look at that again. 32 cos of this, 60, because this is 30, this is 60. 32 cos 60 is 32 sine 30, which is a half. 16 equals 0. because those are the only three forces in that component, isn't it? This one, this component, and the tension component. That's fine. They're in equilibrium, so the resultant force is naught. So mu r then is equal to tension, 6.4, over 2 is 3.2, root 3, minus 16. So that tells us what mu is. Mu is equal to 3.2 root 3 minus 16, all divided by r, which is 24.5128. So mu is equal to then. Now we've got that in the calculator here. That'll be under ants, won't it? So if we just do 3.2 root 3 minus 16 on top divided by ants, we'll get the final answer. So it's 3.2 times the square root of 3 minus 16. Now we need to put that in a bracket rather than press answer, because the answer contains our number. And then we need to divide that by the answer that we had before, the 24.5128, equals 0.4266, 0.4266 minus. So let's have a look here. Let's just check the calculator. 0.4266 dot dot dot, which equals minus 0.427 to three significant figures. Now let's go back up to our picture. Now we've got a problem here because it says 879. So what have we done wrong? Tension of cos of this angle. Everything seems fine to me. I think I see the problem. When I move these two things over, I didn't move the 16, it becomes plus 16, doesn't it? So this becomes plus 16. So I need to change that in my calculator. So let's go back and change that to a plus 16. Luckily I've all got it here. 3.2 times root 3 plus 16 divided by the answer. 24, that doesn't look right because I pressed answer before. So what I need to do now is just delete this and put divided by the 24.5128. There we go. 0.879 to three significant figures. 0.879. So let's just scratch this then, that final calculation, because that minus 16 through it. It just made it all go gobbledygook. But now we're happy that we've checked it. And that's the three significant figures. Okay then, so part 4 now. Determine whether P remains in equilibrium. The string is, Q and the string is now removed. Determine whether the P remains in equilibrium. So let's have a look at this then. This will now be a force F here due to friction. We've got this tension and this component here. Oh, that's removed. So it's simply 32. So resolving forces down the slope. We're going to have 32 cos of this angle, which is 16. 32 cosine 16. Cosine 60. This is 30, this is 60, 32 cos 60. So part 4. When the string is removed, the force, the weight, acting along the line of greatest slope is 32 cos 60, which is equal to 16 newtons. Now the reaction R also, when you go perpendicular to the slope, that was along the slope. If we go perpendicular to the slope, we can see that R is equal to, let's have a look at the picture. The reaction is 32 cos of this, which is cos 30. R is 32 cos 30, which is root 3 over 2, which is 16 root 3. Okay, so the maximum, so mu R, mu R then, the maximum force is equal to 16 root 3 times 0.879, which equals, I've got it here, times it by 16 times by root 3 equals 24.35. And that is greater than 16. So consequently, the particle will remain in place. Will remain in situ or in its position. Okay, that was because the maximum resistance force, which would be mu R, R was equal to this, and the maximum resistance force was calculated to be this. The component of force due to the weight acting down the slope is only 16, so this is much bigger potentially. This is much bigger than this force, so it's going to stay in place, isn't it?